Welcome to the deep dive. Today, we're plunging into something that might just be a radical reevaluation of what makes an AI model truly deep.
It really is. For years, the default assumption has been that depth means stacking more and more layers.
Right, just build it taller. But what if that entire architectural blueprint is, well, fundamentally flawed?
That's the question we're tackling. We're diving into a paradigm shift called nested learning, or NL, and we're drawing heavily on this paper, nested learning, the illusion of deep learning architectures.
The illusion of deep learning, that's a bold title.
It is. The authors argue that simply stacking layers, the standard transformer model, has hit a ceiling. It's just not working anymore, especially when it comes to memory and, crucially, continuous adaptation.
Okay, so the mission for this deep dive is to get under the hood of that claim. The paper says the standard architecture we see, attention block, feed-forward network, repeat, is just a flattened image of a much more complex process.
A flattened image of what they call multi-level optimization. And we need to expose that hidden complexity.
The core issue NL is trying to address seems to be this limitation of static AI. LLMs are, they're incredible after pre-training.
Absolutely stunning. But then they become these static bricks once they're deployed. They can retrieve what they already know, but they really struggle to acquire and integrate genuinely new skills outside of their immediate context window.
And that inability to truly learn over time, that just drastically reduces their effectiveness in any kind of real-time dynamic environment.
Let me try an analogy. Many current LLMs have a memory problem that's kind of like anterograde amnesia.
Okay.
They have this vast, deep knowledge from their past, that's the pre-training, but they can't form robust new long-term memories after that onset, after the training stops.
So all they have is their short-term memory, the current conversation, and this fixed knowledge from years ago.
Exactly. And that is not a sustainable path if we want AI systems that can actually evolve with us.
So if just stacking layers leads to these static, almost amnesic systems, where did the authors look for a better blueprint?
Well, they looked at the one system that does this perfectly, the human brain. Specifically, how biological intelligence achieves truly continual, lifelong learning.
And the secret there is neuroplasticity.
Neuroplasticity, the brain's ability to constantly reorganize itself, forming, strengthening, or weakening connections between neurons. It's always adapting.
So NL models are trying to translate that biological principle into machine learning components. What specific structures does it borrow?
It really boils down to two fundamental ideas from biology. The first is a uniform and reusable structure for making changes.
What do you mean by uniform?
Well, neuroplasticity doesn't require growing a new brain lobe to learn something new, right? It uses uniform mechanisms, like creating a new synapse. So NL mirrors this by breaking down architectures into nested sets of neurons, often just simple, local, deep MLPs. This gives it a common reusable part for learning at all different scales.
Okay, uniformity makes sense for efficiency, but how do these identical blocks create complex, layered thinking? Uniformity usually suggests rigidity.
And that is where the second principle is so critical. It's the multi-timescale update.
Multi-timescale.
Yeah. The brain coordinates all this learning and memory using internal rhythms, brain waves, and there's no single central clock. You have these incredibly slow delta waves, like 0.5 to 4 hertz, that are crucial for deep sleep and memory consolidation.
And on the other end, you have super fast gamma waves.
Exactly, 30 to 100 hertz, associated with intense focus concentration. Different tasks, different speeds.
So if the brain uses different frequencies, slow for consolidating memory, fast for immediate focus, how does nested learning map that onto, artificial parameters in a model?
In an NL model, every component, every level gets its own update frequency. And this is the key. Earlier layers in the processing chain update very quickly on high-frequency cycles. They're handling the immediate, noisy, volatile information.
While the deeper layers,
The deeper layers, the ones meant to integrate stable, long-term knowledge, they update over much longer, slower cycles. It directly mimics that biological process of moving fragile, short-term memories into stable, long-term storage.
this feels like a complete rethink of what depth even means. So let's unpack the mathematical core here. The paper says architectural depth is an illusion.
It is. The real variable, the thing that actually creates complexity, is the internal optimization process, the nested optimization.
So we've been building these skyscrapers of layers.
But nested learning has basically shown that if you look inside the foundation of even simple models, you'd see that those layers were just hiding the real action. 2 or 3 different internal learning systems all running at the same time.
Before we get into the math, the paper also redefines some core ideas from neurophysiology, like the difference between memory and learning. How does it frame that?
So in this context, memory is just any neural uptake caused by an input, an immediate change. But learning is the whole process of acquiring effective and useful memory. It's the mechanism that stabilizes that change so it sticks around.
And the core mechanism for both is associative memory.
That's the bedrock of the whole theory. Associative memory just maps keys to values. But NL argues that all parts of a sequence model are actually associative memory systems, and their job is to compress their own flow of context.
A layer is an associative memory. An optimizer is an associative memory.
That's the claim. In a network, the parameters are mapping an input, which is the key to some desired internal change, the value. It's always a process of context compression.
Okay, let's make this concrete. Let's start with the simplest possible model, a single layer network, and you're training it with standard gradient descent.
Right, so training that one-layer MLP with GD is a single-level optimization, a one-level associative memory. It's mapping data points to their required error signal. They give it a name, the local surprise signal.
The local surprise signal, LSS? That's just a fancy way of saying the mistake the network just made, right? The gap between what it produced and what it was supposed to produce.
Exactly. It's the mismatch, that local error gradient that tells the weights how to change. With standard GD, it's one single unified gradient flow. Very simple.
Okay, now here it is, the aha moment. What happens if we just switch to gradient descent with momentum?
This is where the illusion shatters. This one simple addition reveals a two-level optimization problem hiding in plain sight.
2 levels. How?
The momentum term isn't just a simple tweak to speed things up. It's acting as an inner-level associative memory. It's literally learning to store and compress the history of past gradients into its own temporary parameters. This is the fast network.
So momentum is its own little memory system updating super quickly.
Yes. And then the outer level, the main process, uses that compressed history from the fast momentum network to slowly, carefully update the main long-term weights.
And this fast wait, this temporary memory update, is that what people have been calling fast wait programs or FWPs?
It's essentially the same idea. Yes, FWPs are all about having these temporary, rapidly updated weights that exist alongside the main slow weights. And that's precisely what momentum is doing. It's storing these temporary, fast-decaying memories of the gradient flow.
So the complexity was never in the number of layers. It was in these nested memory systems.
Exactly. And the NL framework shows this applies to the architecture itself too, not just the optimizers. Take something like linear attention, a core piece of many modern models.
Okay.
Linear attention can be mathematically broken down into a two-level optimization. The projection layers, the key, value, and query weights, those are the slow weights. They only update in the main training loop, integrating knowledge over the long term.
The inner part.
The internal memory matrix update, where you're multiplying the current key and value vectors together at every single step. That's the fast wait update. That's the inner loop optimization happening rapidly for every single token you process.
So NL gives us this clear mathematical way to define depth based on update frequency, which they call 5all. This is a white box definition, not just counting layers.
It's a proper formal definition. Components are ordered into levels based on how often they update. If you update less often, you are a higher level component. You integrate information more slowly. It ties the math perfectly back to that biological multi-timescale concept.
Okay, so if optimizers are actually meta-memory modules compressing gradients, this just opens the floodgates for designing better, deeper optimizers. How do we make that momentum term, that inner memory, more expressive?
Right. The standard momentum term is just a simple linear association, so it's limited. NL points to 2 ways we can improve it. First, by using more expressive association, and that means preconditioning.
What does preconditioning add to that memory?
Well, instead of just compressing a raw stream of gradients, the momentum term is now asked to map preconditioning parameters to the gradient. Now, those parameters contain rich information, maybe about the curvature of the loss surface, like data from the Hessian matrix.
Ah, I see.
The associative memory now has a much more meaningful, high-context mapping to work with, not just a sequence of numbers.
And the second extension goes even further, creating what they call deep momentum gradient descent, or DMGD.
Yeah, this is really cool. So instead of using a simple linear matrix for the momentum's memory, which can only really capture straight-line trends, DMGD replaces that memory with an MLP, a multi-layer perceptron.
You put a neural network inside the optimizer.
You do. By making the memory nonlinear, you give the momentum term the ability to recognize much more complex curved patterns in how the gradients are changing over time. It gets a much better predictive power.
This whole intellectual breakthrough also led to a real architectural component, right? The Continuum Memory System, or CMS. And this was built specifically to fix the amnesia problem in LLMs.
That's right. The CMS is basically a chain of MLP blocks, but here's the difference. Each block is fundamentally distinct because it's associated with its own unique update frequency and a specific chunk size for how it updates its parameters.
So we're not just stacking identical blocks anymore. We're stacking memory systems that all operate at different speeds.
Precisely. This is the physical implementation of that multi-timescale idea.
Hmm.
A conventional transformer block with its single feed-forward network is just a really simple special case of a CMS where you only have one frequency level.
Only one speed.
CMS just explodes that potential,
Yeah.
allowing for all these different levels of knowledge abstraction and different timescales.
Okay, let's talk about the implementation. The paper introduces a model called HOPE-PA, the Hyperorder Predictive Engine, which puts all these NL ideas together.
HOPE is a self-referential sequence model building on some older recurrent architectures like Titans, but with the CNS integrated right into its core. And the critical change is that the standard FFN in the transformer block gets replaced
Replaced with what?
with a series of FFN layers that all operate at different distinct frequencies. You have a low-frequency layer, mid-frequency layer, a high-frequency layer, and so on.
So the model's persistent knowledge isn't a static snapshot anymore. It's a dynamic system where different pieces of knowledge are stabilized and integrated at different rates, just like memory consolidation in our brains.
Yes. And this multi-frequency design is coupled with the self-referential nature of the attention, which lets the model dynamically adjust its key, value, and query projections based on the immediate context. It gives it incredible flexibility.
So the big question, does this philosophical and structural overhaul actually work? What did the evidence show? How did HOPE perform?
The results were very promising. They tested it at scales up to 1.3 billion parameters, and HOPE showed significantly stronger performance than a lot of very strong modern baselines.
Models like Transformer, ++BretNet.
Transform++ RetNet, DeltaNet, Titans, it outperformed them.
And we saw better language modeling, so lower perplexity, and importantly, big jumps in accuracy on those common sense reasoning and long context tasks. Things like PQA, HelloSwag, Wanna Grande, Bulky.
Yes, and the key finding in the paper is that these improvements weren't just from making the network bigger. They were directly attributable to this architectural shift, the dynamic updates, the multi-frequency layers, and that deep memory module, the CMS. By actually designing for these nested optimization problems, the models got better at continual learning and abstract reasoning.
So let's bring it all home. What does this mean for the future of AI architecture? We started by questioning if deep just meant stacking layers. Nested learning seems to say a definitive no.
It says the true power is in the internal gradient flows, the multi-level optimization problems that we can now expose and design. Problems that mimic the brain's own multi-timescale memory consolidation.
NL feels like a transition mechanism then.
I think so. It moves ML models away from being static amnesic systems and toward becoming dynamic, self-modifying, continually learning systems. And it does this by forcing us to see every single component, from the momentum term to the attention block, as its own unique associative memory, defined by its own update frequency and context.
Which suggests the next big frontier in architecture isn't just scaling size or scaling the number of layers. It's about scaling the number of distinct levels or frequencies within this nested learning structure.
And it leaves you with a really powerful question to think about. If we can formally design and train models with, say, 4 or 5 deep nested memory systems all running at wildly different speeds, what kind of capabilities will unlock when a model can truly self-modify its entire learning algorithm on the fly? We'd encourage you to look deeper into the connection between these deep optimizers and fast weight programs. It really seems that optimizing for memory, not just size, is the path